Today I'm going to be covering forward selection and backward elimination methods for model selection. So that is something that you guys have in your assignment. So what you guys will be doing in your assignment is you guys will be just using the step function. So that's one of the automatic model selection functions that's inbuilt in R. That will do the forward and backward elimination processes for you. But what I'm going to teach today is an iterative step. I'm going to make you understand step by step how to do a forward selection or a backward elimination. What do you guys know about model selection? What did your professor handle in class about forward selection and backward elimination? Couple of points. Anyone? Not much. Mhm. So, it's essentially model selection. It's for example, you have a variable that's to be predicted, a y variable, right? So what set of predictors best predict the y variable? Or how do I add certain variables? So that's what is model selection is about. At the end of the day, I'd want my y to be predicted by my best predictor variable. So model selection takes care of this, and though there are a couple of inbuilt functions like at the end of the day, when you do a step function or a rate subset function, you're just going to see the output and how did we arrive at that model. So the iterative step is something that's going to teach you that. First of all, you need to. Okay, so I haven't uploaded this R script yet on GitHub, but what there is this data set called soft drinks that I have uploaded to the usual um, link, right? So you have the 371G master data. So you just need to copy that, and the last thing is just softdrinks.csv. So I recommend you guys to load this data set. So actually, this entire data set consists of a lot of unnecessary variables that you guys do not need right now. So you would be better off if you could add this clause over here so that it picks the variables that we want, the columns that we want. So go back. Make sure you install the package leaps, and make sure you load the library fpp2 as well. So that's the first thing to be done. Okay, it's already installed. So um, okay, so leaps has been installed, and I'm gonna load this soft drinks dataset now. After I've done that, I'm gonna view this soft drinks dataset. So this is what this data set is about. So it's like this: you have a product. So my aim is to analyze for the sales of X. which are basically binary variables, which indicate if there is a deal or if there is a promotion that's been run on X and ounce Y obviously indicates the uh, amount of uh, so what I'm going to be interested in finding is what set of predictor variables best explain the sales of product. So that's what this data set is about. So the variables in the model are as follows. Px is the price of your product. Py is the price of your competitor's product. Deal X implies there's a promotion on X, and similarly deal Y. Ounce X are the sales of the product X. This variable is the Y in our model. That is, I'm going to be using ounce X as my Y variable in my regression model. Uh, uh, so another thing, I'm not going to be using ounce Y as a predictor variable for this session because I um, however, the aim of today's session is to apply forward selection and backward elimination to predict log of ounce X. So that's what I'm predicting. I'm not predicting against the law against deal X, deal Y, log of price of X, log of price of Y, interaction X, which is basically an interaction variable of deal X times log of PX, and an interaction Y variable, which is the deal Y times log of PY. So all these are variables that I'm going to consider. So my X variables for my full model, that is the full model, which may be or may not be the correct model. But my full model would be log OZX against deal X plus deal Y plus log PX plus log PY plus interaction X plus interaction Y. That's going to be my full model. So we'll get down to that. So since you can see here from the data set that none of the variables have been log transformed yet. You guys know enough of the log transformations and the better fits. Just how I arrived at it. So I'm going to directly be doing the log transformation for first OZX. So I'm going to call that log variable as L dot YX. That's nothing but log of the OZX variable. So I run that. Then I have log of price of X, which is L dot PX. Then I have L dot PY, which is the log of price of Y. Then I have deal X variable and PY variables. Then I have the interaction X variable and the interaction Y variable, which is deal times the log of price. So I'm loading all these data now. So you can see here in your global environment that you have all these variables included, right? Also note that this is actually quite a big data set in the sense that it has around 728 entries. So if it takes a little while on your computer to load, it's absolutely fine. So first you have the full regression linear regression. Like I said, the full model would just be an LM statement regressing your L dot YX against deal X, deal Y, L dot PX, L dot PY, interaction X, and interaction Y. So let me run that first. So the first step to be carried out in any I'll run the full model now, and that's the summary of the full model. You can actually infer a couple of things from here. Can anyone tell me what you can infer from the backward elimination? But before that, I'll run the null model as well. So the null model, like I said, is just regressing your y variable against 1 without any other predictor variable. So I'll be doing that. All right. So that's my null model. Now, the null model doesn't you know like significance to the null model. So I have something called information indices. So um, you guys have done and then yes. So um, command to use than the AIC. But if your class wants you to use AIC, it's simple. You can just use the AIC. But I'm interested in comparing various different information criterion, so I'm going to be using the CV command. So first, what I'm doing is are you guys familiar with what the command rbind model next to in, in right? Uh, we call this these what do we get right like BIC AIC named it as INF IND1, which is it's an rbind command. Uh, it has the CV of the null model and the CV of the full model. So I'm going to be comparing, say, the AIC values of null model and the full model using this. So you'll see how it works. I'm just going to give row names to this information indices, saying this is the null model and that's the full model. And I'm printing the information indices. So what the rbind command has done does it need to be low? As compared to your R squared values, which need to be high. So you can see that the null model's AIC is minus. Okay, so that's taking the negative into account as well. So if I have something like 66 and 2 to 3, So all I've done now is I've compared the full model and the null model using the rbind command, right? So we'll actually get down to business with backward elimination. So what backward elimination does is, like you said, um, I first found the full model. I saw that a couple of predictor variables were useless in the sense that they had very high p values. So I'm going to eliminate one of those, right? I'm going to start from there, and what I'm going to do is I'm going to, at every So, the first iteration of the backward elimination process is we saw that from the full model. I'll show you again. You saw two useless predictor variables in deal y and interaction y, right? So I'm going to be dropping the variable deal y from my full model because it has the highest p value. It has 0.88450 as compared to interaction y, which has 0.881, right? So I'll remove the variable deal y. So my reduced model 1 will have yx, lyx predicted against everything else other than deal y. So I've removed deal y from the model now. I run the model, I get the summary. There is not much change in the multiple r squared value, but obviously you can see that interaction y is still a useless predictor. It's not significant. So that's the next step that we're going to be doing. The second step is where you eliminate that variable. But before that, what I do is now I'd like to compare the information analysis of all the three models that I've done so far. So I'm going to be comparing null model, full model, and the first reduced model. So I use the rbind statement again. I print the row names and the information analysis. So what can you observe? Um, we can see that the AICC index has decreased. Now I'm going to be removing interaction y because we saw that that was the other predictor variable that was not significant. So I do this reduce model 2, which just involve dlex, lpx, lpy, and interaction x terms. I'm getting the summary of that model. What can you see from here now? Um, Again, I'm going to be printing the information indices. Now I'm going to be comparing everything, null, full, reduced 1, and reduced 2. I print the row names. I print the indices. You can see that it has further decreased. I'm going to be continuing this. Now, what I do is, which one is the lesser significant of all these? Can you tell me? I mean, I know all these are statistically significant now, but the Lex is something that I could eliminate still, right? Because that has a higher p-values than the other. So that's what I'm removing here. In reduced model 3, I do not have the Lex. I'm removing that, running it, printing the information indices. Right. What do you see? Elimination. You have derived at a model, and that model would be this, right? Deal X, Px, Py, and interaction X. V1 response. So let me cross verify this now with the forward selection process. So if I run a forward selection process, I should be getting, I mean, logically speaking, I should be getting the same model as the best model. So what do you guys think? With at every iteration, what I'm going to do is at every iteration, now I have the null model. At every iteration, so the forward selection is an even lengthier procedure in the sense that you need to add every variable one by one into the model, and this is going to be one iteration, right? So I have for each iteration, so it's definitely a longer process, which is why you generally use the step function. But I wanted you to understand why how the step function works. So hence the iterations. So yeah, the forward model one. So I did not know. I'm arbitrarily taking LPX as my the first choice. I'm just arbitrarily taking. I'm going to be regressing LYX against all my predictor variables one by one and seeing which has the highest R square. So this is my forward model one. Summary, right? So I have added LPX now. I can see that the multiple R squared value for this one is 0.8519. Fair enough. I'm going to be okay. So also what I'd like to do is I'd like to print the information indices for my null model and my forward models starting from here. So I'll do that. Okay. Okay. Or rather, what I can say is I did not do. Okay, so now we go to the actual iteration that is adding the second predictor to the model. Now I know that LPX is there in my model. I'm going to be adding every other predictor variable one by one and checking for the aspect. I do that. Okay, so that's my forward model 2. It's 8552, right? I'm going to be running forward model 3, 9414, which means adding, where was I? Right, forward model 3. So, which means adding deal X instead of LPY makes more sense right now. So, I'm going to be keeping model 3 as my best model for now. Model 4, 9414, that was. This is 0.8557, which means model 3 is still the better model. Forward model 5, 9414, this is 942, which means that forward model 5 is a better model right now. And forward model 6, I don't think this. Yeah, so it's 8558. So from the first iteration, I've added the second predictor variable, interaction X. Now I'm going to keep these two constant, and I'm going to be adding the rest of the variables as my third predictor variable. So before that, like I said, at the end of every iteration, what I do is I compare the information indices. So I get here. Yes. So forward 1 and forward 2. Give me just a second. Huh. Okay. Okay. So it's better I compare all my iterations. So okay, I'll just say find functions. It's just a minute to figure this out. Okay. Oh, it's okay. So yeah, I'm going to be comparing all my indices again. So I can see that my indices have decreased again. Even for the first variable selection, right? Uh, Even for adding the first predictor to my model, I should have tested everything. But I took it for granted that LPX is my first variable. So I should have actually done an iteration there as well. So you understand yes, I mean, you don't need, I mean, about this. So now I have the iteration 1. Okay, this is done, right? Okay, so now the iteration 2, right? I'm adding the third predictor to the model. I'm getting the summary. It's 0.9491 with when I add LPY to the model. When I add deal X to the model, it's 9426. When I add deal Y to the model, it's 9474, which means that I am going to be adding LPY to the model. I actually have one more model to go. So this is 9474 again. So I'm going to be adding LPY to the model. So and at the end of this iteration again, I perform uh, uh, I print the information indices, and I see that from forward 2, it's still further decreased to forward 3. So I'm going to be still going. Now I'm adding fourth predictor to the model. So it's a very huge iteration, but I hope you guys get more clarity than using the step function. This gives you more clarity as to how you actually select the model. So this is exactly what the step function does, but it does that internally and it just churns out the output for you. So you don't know how it selected the model. So yeah, word model 11. Perfect. Okay, so that's 9499. This is adding the fourth predictor to the model. So yes, yeah. So I'm going to be adding deal x as my fourth predictor to the model. Now I have four predictors: LPX, interaction x, LPY, and deal x, which you can, if you notice from the backward elimination. I can expect that when I print this out now, it has decreased. But if I go one further iteration, this ASE and ASCC values are going to start increasing again. So you can expect that. Now, if I add the fifth predictor to the model, I'm going to be doing that. So you can observe that these actually have the same R squared values. So if you have the same R squared values, you can arbitrarily choose any of them. And so I've added deal Y because of that. And I'm printing out final information indices. What do I observe? It started to go up again. So the actual model is now model 11, which is uh, price of X, interaction X, price of Y, and deal X. Remember this because you'd want your step function to come up with the same result. Perfect. Okay. So I'm performing the step function now. Okay, so I'm going to be performing it in two ways, right? So I'm going to be performing it in the forward direction and the backward direction. I mean, these two statements is all you need to do. Yeah, you start with a null model for your forward, and the scope is a list of a lower and upper model. The scope function, what it does is the scope clause will uh, take care of all models from your null model to your full model. It will iterate everything by itself. So lower is the null model and upper is the full model. Direction is forward. Yeah. So I ended up with the same. I ended up with the same model that I did in the iterative. And similarly, if I carry out the step function for the backward direction, so now my first model will be my full model. I'm going to be reducing the model. So the lower is a null model and the upper is a full model. And direction backward, and I get the same result. So the step function is one of the automatic ways to. So the reg subset function can be used in three different ways. What so the so I'm going to let the reg subsets select automatically using the NVMax option. So I'm naming it as subset auto. Is reg subset of. I'm going to be adding all my predictor variables right now. I've added everything, and data equals soft drinks, and NVMax equals 4. So that's run. And if I get the summary of that, okay. So Okay, this is all you need to look at. What can you look at? Next is okay. So reg subsets can also use the backward elimination and the forward selection ways of doing it. So now you're not going to be specifying what's the number of predictor variables you want in your model. Rather, you're going to let the model, let the reg subsets function choose how many predictor variables it can hold in the model based on backward elimination and forward selection. So instead of giving the nvmax clause, I'm going to just be giving method equals backward. So I'm starting with the full model. I'm giving method equal to backward. Oh, okay. See what it's done here. And rig subsets using forward selection works the same way. Yeah. You essentially should, all these are like cross validation. Do you remember? Backward elimination, right? Mm, this one? This one? It has, right? CV has gone down from 0.046 to 0.045. Not so significantly. We can help you with your homework in case you have any doubts. But yeah, hope you guys understand forward selection and backward elimination. Okay, awesome.